Hello, everyone. Today I'm going to present our paper, Countering Multimodal Representation Collapse through Rank-Targeted Fusion. First, let's talk about the definition of multimodality. We humans understand the word from diverse source modalities. For example, we can hear voice through ears. We can see the presentation visual through eyes, and we can read the text in the presentation. Similarly, when AI understands human actions, it gets information from RGB, depths, in-store sensor, or physiological signals and predict the action. Then what would be the benefits of taking these many modalities into account when making a decision? The benefit is that each modality has its own features that is unique to each modality. For example, RGB excels at representing texture, shape, and color, while depth excels at representing direction, structure, and position. These features complement other modalities' features, so AI ideally can get all the informations about these features by doing this multimodal fusion. So this is the biggest benefit of multimodal fusion. Now let's simplify this and just think about the multimodal fusion with RGB video and depth. Ideally, AI wants to get all the different features from these two modalities. However, one of the challenges in multimodal fusion is that the AI can only see the partial information. For example, AI may only focuses on dominant information and ignores others. For example, in this case, when AI sees the video, it only interprets as a combination of blue, black, and white information, which is color. And when it interprets the 3D depths, it just sees the direction and ignores other features. We call this as feature collapse, meaning that it only focuses on dominant features only and ignores other features. Another case is that AI only relies on certain modality. For example, even though video and depth comes, AI only gets information from RGB video. We call this as modality collapse, meaning that it only preserves single modality and ignores others. So in this presentation, we will address two problem statements. First, how can we ideally fuse these different modalities to counter this feature collapse and modality collapse? Also, since there are many different modalities like depth, IMU, and RGB, text and RGB, which combination should we use to best counter collapse? First, we will address how to ideally fuse different modalities. We approach this from an information theory perspective. If we take a feature matrix and perform SVD, singular value decomposition, what SVD shows us is that how much each singular vector contributes to the representation space. After we do the SVD, we can calculate the rank. The rank is the number of the non-zero singular values. The rank shows how many independent directions the representation spans. If only one or two directions dominate, we call that representation as low dimensional and less expressive representation. Eventually, we want our representation has diverse features as possible. So we use effective rank, which captures how evenly the singular values are distributed. For example, the collapse case in the left side means that the representation is only concentrated in limited directions. Conversely, the diverse case in the right side means that the representation spreads information across multiple directions. So if the effective rank is high, then the eigenvalues are more evenly distributed across principal indices as like the green case. We regard this green representation matrix as more informative because its effective rank is higher than the red representation matrix. Now, let's say we have this RGB video. If we feed these into our RGB encoder, we can get many channels. Then we want to know how much each channel contributes to the information content of the representation matrix. We refer to channel that contribute more to the representation matrix's information content as informative channel. Similarly, we call the less contributing channel as less informative channel, as this channel contains less information about the representation space. To figure out informative and less informative channel, we calculate how much each channel contributes to the top K dominant features. So after RGB and depth video is encoded separately, we get the channels from each encoders. Then we calculate the informativeness of each channel with the right equation. Then we selectively target the less informative channels. Once we tell what is less informative channel, instead of using everything, we blend those less informative channel with those of other modalities with learnable parameter alpha. And we use this fuse matrix to solve the downstream tasks. We propose this fusion method as targeted information fusion since we target some less informative channels and specifically blend those to increase the feature diversity. Now we know that how to fuse different modality by preserving all informativeness. We need to also consider which modalities can complement best each other. So in this case, our goal is to see if each modality gain feature diversity after fusion. So for example, if we see in this case, RGB preserved all the features and also got the feature diversity because of depth. But in this case, RGB loses some of its features after fusion. In this case, text modality preserves all of its features and also gains feature diversity after fusion. But if we see it in RGB's perspective, RGB loses some of its features after fusion. So ideally, we are finding a modality pair that can mutually increase the feature diversity for both modalities. To consider this mutual gain for both modalities, we adopt the harmonic mean because the harmonic mean examines how evenly both modalities improve their feature diversity, as we discussed in the left side. In the right side, we plot all harmonic mean calculations for 4 pairs of modality pairs for different video observation rate. We can conclude that RGB plus depth pair best improves representational diversity for both modalities in all observation rates. So we adopted the RGB plus depth modality pair for our experiment. We evaluated our proposed methods in diverse experiment setups. First, we examine our model in the 2 different downstream tasks. Second, we show if our method counter feature collapse and also modality collapse. Then we also see if the proposed method is robust enough, so we evaluate in various forms of noise perturbation settings. When we apply this fusion strategy, we see state-of-the-art result on action anticipation benchmarks. We also observe strong performance improvements on action segmentation tasks across multiple datasets. We also analyze each modality's feature diversity before and after fusion. Left side is RGB's before and after fusion feature diversity, and right side is depth modality's feature diversity before and after fusion. We show that in both modality, feature diversity is increased. This is because we target the less informative feature and blend those specifically during fusion. We also compare with other existing methods. In the left side, our fusion method leads to increased feature diversity for both two modalities, whereas in the existing method, RGB's modality's feature diversity has decreased after fusion. Lastly, we also conduct the robustness test in various noisy settings. We set clean, small noise, and add big noises. Our fusion methods were robust in both three settings, whereas without our targeted fusion, the anticipation performance drops significantly by the amount of noise. In conclusion, we present R3D, a depth-informative framework for action anticipation that addresses true representation collapse, which is feature collapse and modality collapse in multimodal fusion. We are the first to formulate this multimodal fusion as a problem of rank-targeted fusion. And our R3D achieves up to 3.74 performance improvement on various datasets. This is the end of our presentation. Thank you for listening to our presentation.